Okay, the next gas law that we have to be concerned with is one of my favorites is actually Charles' law. And there is Charles' law basically came about because there was shown to be a relationship between V and T, so volume and temperature, when the gas pressure was held constant. And Charles' law came up with this. The scientist Charles came up. So, as I mentioned, there is a direct relationship between the temperature of a volume of gas, and if one increases, so does the other. So here's our linear relationship here. So it's pretty much a linear relationship. So as one increases, as the volume increases here, right, then the temperature also increases. So it's a direct relationship. Unlike Boyle's law, where there was an inverse relationship, in this case, as one of the constants, or one of the variables increases this way, the other variable increases in the same way as far as increasing in magnitude. So that's why there is a direct relationship as opposed to an indirect relationship between temperature and volume of a gas. If one increases, so does the other. And we must make sure that we understand that we need to hold pressure constant. Otherwise, Charles' law is invalid, right? Because now we're changing all three variables. And if we look at this very closely, right, you can see that V1 over T1 is equal to V2 over T2. Or you could write it a different way, that V1, V over T is going to be a constant, right? So when one increases, the other increases, and our constant slope there is what it is, right? And you could also just basically write this as V is a constant times T, where constant is the constant is the slope of the line. So other than that, there's really nothing significantly challenging about this relationship. So it's similar to Boyle's law as far as complexity, but it's really not complex at all. And the key thing, though, is, and this I'm going to underline or highlight this a million times, is that all the temperatures must be in degrees Kelvin or Kelvin. So I'm going to keep circling this until the cows come home, because I know that students will make this mistake at some point in their careers. I know I did. And so you need to convert everything first in Kelvin. Normally we don't give you Kelvin. We will give you like degrees C, because that's what we normally measure. There's not many thermometers that are made for Kelvin. So everything goes into C, and then you need to convert it to Kelvin. And we already know how to do that. As far as the kinetic molecular theory of gases, as the temperature decreases, the particles move slower, causing less collisions, and therefore the volume will decrease, right? So they don't have to go as far with the energy, right? So if they reduce in energy, then their distance traveled is not that far, and therefore they don't need to have that much volume to travel in. So otherwise, it's pretty much the same as that. So if you increase the temperature, obviously you're increasing kinetic energy, which increases the translation of the particles inside the space. So they'll go farther, travel farther as they're with their increased energy. So they need more volume to accommodate that increased distance. So this is going to be fairly short, but let's just look at a couple examples here real quick. And I left all the numbers on here to calculate, just to kind of walk through real quick how to do this. I don't think this requires much thought, as opposed to just solving in the equation. And we'll probably always give you at least three. We'll have to give you 3 out of the 4 variables in this to solve for Charles' law right here. 3 out of the 4. So we might give you V1, T1, and a V2. And you might have to calculate T2, or the other way around. We might give you V1, V2, T2, and actually calculate T1. Any combination of that, right? And an example of how Charles' law works is, remember back to the lab, or the demonstration I did in class, where we heated the can up with very hot steam, and then I closed the can, and as the gas in the can cooled, the volume had to shrink also, because now the gas is no longer occupying that whole thing, and it shrinks. And then why does the can implode? Is because as the volume shrinks, it needs to pull in the can, and we have the pressure on the outside of the can to help do that until the pressures on the inside are equal. So that's pretty much the thing that happens here. So let's look at this pretty closely here, just to get everybody back onto where we need to be. And so here we go. So we giving a initial volume of 15 liters. If the temperature increases from 330 C to 450 C, find that 330 C to 450 C, find the new volume, right? So it's pretty much a standard equation. So let's get our writing instrument out here and say that, so here's our V1, so this value will be here. And then our T1, remember we have to convert it to degrees Kelvin. So we add 273 to 330, and we get a T1 is equal to K, and that'll go here. And then we don't know what V2 is, so that's what we're trying to solve for this. And then we know that T2 is going to be this number because, again, 450C plus 273 will go here. And then you could rewrite this whole equation to say that V2 equals V1 times T2 over T1. And kind of the same, simple as this over here. Here's our V2, right? And if you flip that around, you can get the same thing I just did. You can move this up to here, and you'll get that value. And then the answer would be 18 liters, right? So in liters, so we started out on 15, and now we're at 18. And it makes sense because we've increased the temperature from here to here, so you should expect an increase in volume. And that's pretty much the simplistic side of how to solve these equations. There's nothing more. There's nothing complicated about it. The only thing that's really complicated is to make sure that the temperatures are always in degree K. So that's the only thing that's really complicated on this. Anything else is pretty much not that complicated. And again, another practice thing here just to make sure that we understand what's going on. So we have a quantity of gas that has a volume of 254 milliliters, right? And then it's at 27 degrees C. And then when the temperature, we drop the temperature. So this is kind of what we did in the lab for with the crushed can. When we drop the temperature to 17 degrees C, the volume and at constant pressure, the volume has to be, and then so we expect the volume to decrease because if T1 is going to T2 as reducing to T2, so let's make that if T2 is less than T1, then we would expect that V2 would be less than V1, right? So there we go. So that's the basic thing we're expecting here. So let's just look at the thing here, and let's just erase all this. And so what we have here is we have 254. So that's going to be our V1 for the first one. Let's put that here, and then 27 degrees C. Now make sure we convert that to degrees Celsius, so that'll be 300, right? So we have the 300, and that's K, and so that's 300 K. So make sure I get that all in the thing. And I'm doing it below here too, but I'm just showing you where I'm getting this information from. So 300 K, and that's going to be going to here in the T, and then the last thing I need is 17 degrees C, and that value, when we convert it to K, will go in this spot here. Right, and then we're just left over. So here's the equation rewritten it's our pre-written, and then you solve it, and so you should get roughly 246 milliliters, right? If we did that correctly. So we could do that again, but we should get 246. It's going to be less than 254, but it's not going to be much less than 254 because we've only dropped the temperature here by 10 degree K over 300 degrees. So it's about 3% more or less. So it should be about 246, and that is the correct answer. So to just wrap up Charles' law with this last little statement here, and you should be able to figure this one out on your own, but I'm just going to quickly walk through it. A sample of gas is held at a constant pressure. So we have constant pressure, so that means that Boyle's law does not apply here. And increasing the Kelvin temperature of this gas causes the average kinetic energy of its molecules too. And we know already that kinetic energy is proportional to T. So as T goes up, so does the kinetic energy, and so we expect the kinetic energy to increase if we increase the temperature, right? So anything that we see here that says decrease is probably not going to be right. So we're just going to X that out and X that out, and then we also know from Charles' law that the volume is directly proportional to T. So as the volume increases, so does T, or vice versa. So anything that has volume increasing with T increasing is probably a good answer. So we have increase N, the volume of the gas sample, to decrease. So we don't expect that. So the kinetic energy is increasing, but the volume is not decreasing. So that's out. And then the last one on here is increase in the volume of the gas is to increase. And that is our correct answer for those of you that did. So that's pretty much it for Charles' law in a nutshell. Nothing too complicated, nothing too special, but it is a powerful law in it's one of the three main laws that build up what we call the ideal gas law and also the combined law. So it's part of that. You should understand how it works in relation to other things.